All right. Thanks very much for the opportunity to speak, and thanks very much to Jeremy, Peta, and Andy for the invitation to do so. All right, so this is a talk on second-order terms in arithmetic statistics. This is a very much ongoing work, so I'll definitely be reporting on work in progress, and it's a joint with Alexander Berglund, Greg Michael, and Tritang Tran. Right, so what I want to do to begin is speak a bit about arithmetic statistical questions in number fields, so classical questions that arise in number theory, and then with the aim of trying to adapt these problems over number fields into problems over function fields, where they can often be expressed as point counting problems on various moduli spaces. So, all right, let me begin with one of the simpler ones to state from number theory, which is really just about counting the number of number fields of a particular degree. So what do? We let n be a positive integer, and we pick numbers a and b, and we'll ask that a is less than b, and we'll define n sub n of ab to be the cardinality of the set of number fields whose degree is that number n and whose discriminant is bounded between a and b. Obviously, this set is empty if a and b are too close to each other, and so the problem is about sort of studying the behavior of this quantity as b tends to infinity, or as a tends to minus infinity, or things of that nature. So perhaps, unsurprisingly, like we sort of imagine that the number of number fields of a given degree, of degree n, is probably infinite. This is asking a somewhat more refined question of how does that quantity vary as a function of the discriminant. And there's a conjecture which I've been told is sort of due to Linux or possibly apocryphal, which is that this quantity is asymptotically linear in the bounds a and b. So when n is equal to 2, this is a somewhat classical phenomenon. So here we're asking about the number of quadratic number fields whose discriminant is bounded between x and minus x. And since the discriminant, a quadratic number field is specified by adjoining to the rational numbers the square root of some square-free integer, really what we're doing is asking about the number of square-free integers with the property that the discriminant of the associated number field is bounded between minus x and x, or bounded in absolute value by the quantity x. But again, since the discriminant of that number field is approximately equal to the number that we've adjoined the square root of, so it's either that or it's the 4 times that, depending upon what that square-free integer is modulo 4. So since it's basically the since the discriminant of that number field is basically the integer whose square root we've adjoined to the field, this is really basically like counting the number of square-free integers between minus x and x. But since the density of square-free integers is 1 on zeta of 2, that quantity is x on zeta of 2. All right, so this result was extended to cubic fields by Davenport and Heilbronn, and then to quartic and quintic fields by Bhargava. And these are, I think Davenport and Heilbronn was in the 60s or 70s, and Bhargava was in the 2000s. All right, so we can make more refined variants on this conjecture by adding some further data. So if in addition to asking about the number of number fields whose degree is n and whose discriminant is bounded in some way, we could also insist that the Galois group be a particular specified group. So how we do this is say we let G be a subgroup of Sn, and we insist that it's a transitive subgroup. It acts transitively on the n tuples, the set of n elements. Then n sub G n of AB is going to count the number of number fields whose degree is n, whose discriminant is bounded between a and b, and whose Galois group is isomorphic to G, where here the Galois group is the Galois group really of the Galois closure of that field. And furthermore, the isomorphism is an isomorphism of permutation groups, because the Galois group, of course, acts on the set of embeddings of the number field into its algebraic closure. There are n embeddings since it's a degree n extension. So that gives us a representation of the Galois group on a set with n elements, and we want that representation to be the same or conjugate to the representation given by the inclusion of G into Sn. All right, so that's a variant on this, and obviously if we add up over all G, which are transitive subgroups of Sn, we'll get the previous quantity. Okay. So a conjecture of Mala predicts the asymptotics of this function when a and b are the same, are opposites, and so we're bounding the discriminant in absolute value. And along with Jordan Ellenberg and Tri-Tan Tran, we proved the upper bound in Mala's conjecture if we trade the problem over number fields for a problem over function fields. And furthermore, if the function field is fqt, then we insist that the cardinality of G and Q are coprime, and that Q is sufficiently large relative to some quantity, capital Q, which depends upon G. I should note that we don't expect that bound is really necessary, but it is certainly necessary for our proof. So I don't want to talk too much about this result. I'll need to talk a little bit about it in order to get to where we're going. Instead, I want to talk about more refined results about second-order terms in these counting problems. So let's return to the number field setting. This is a really neat theorem of almost at the same time Takashi Taniguchi and Frank Thorne, as well as Manjul Bhargava, Arul Shankar, and Jacob Tsimerman. So what they do is they count the number of cubic fields, just this n3 of 0x. Here I guess we're counting them with the positive discriminant, which is bounded by x. There's a similar version for negative discriminants as well. And indeed, as Linnick conjectured and as Davenport and Heilbronn prove, the leading term here is linear, and the constant in front of it is 1 on 12 zeta of 3. But what Taniguchi-Thorne, Bhargava-Shankar, and Tsimerman prove is a computation of what the second order term is. And it's a complicated constant times x to the 5/6. That complicated constant involves the zeta function and the gamma function. And I'm sure that there's a number theorist could look at this and learn a lot from that expression, but it's a bit forbidding to me. And they proved that the error in that in the approximation of the correct answer by the first and second order term grows at worst. That's supposed to be a negative 1 on 48 away from the x to the 5/6 term. All right, so the moral of that story, at the very least for the purposes of this talk, is that the second order term for counting cubic fields is of the form x to the 5/6. So what I'd like to talk about today is the analogous problem in the function field setting. So to do this, let me talk a little bit about the method of the work with Ellenberg and Tran, and about how we're going to adapt those techniques to studying second order terms. So the method is, the first step is to say, well, in counting number fields, when counting field extensions, not of number fields, but of function fields, of fqt, with specified discriminant and specified Galois group, you can identify the set of these things as the fq points of a Hurwitz moduli space. Really, it's a moduli stack. So let's write Hur sub gn upper c of the field k to be the set which enumerates isomorphism classes of surfaces, sorry, not surfaces, of algebraic curves over K, mapping to the affine line over K, whose Galois group, whose group of deck transformations, or automorphism group of the map pi, is isomorphic to G, and for which there are exactly n branch points of the fibration, sorry, not the fibration, of the map pi over an algebraic closure of K. And indeed, around, at each of those points of the branch locus, that the monodromy of the cover is in a particular subset C of G. So we do this because we can. It's not entirely necessary, but what we're doing is asking for even further refined information about the kind of monodromy that's occurring in these extensions. So for instance, if G is the symmetric group, we could take C to be the conjugacy class of transpositions, and here we would be enumerating the set of simply branched degree n covers of the affine line. All right, so this is a moduli stack, and it's very mildly stacky. It's only an orbifold, but our plan then is to bound the ranks of the homology of these spaces with rational coefficients, and well, really with L-adic coefficients. But of course, these things are the rank of these things is the same as the ranks with rational coefficients. And then by the Artin comparison theorem, we will be able to identify that with the étale cohomology of these schemes, and then we can use the Grothendieck-Lefschetz fixed point theorem to get some control over the point count of these the FQ points of these schemes when we also input the Deligne bounds on the eigenvalues of Frobenius. So in short, if we've got control over the ranks of the rational homology of these schemes, then the Weil conjectures give us some bounds on the point counts over FQ. All right, so that's the general method for approaching these things. Our work in the paper with Tritang and Jordan was to bound the ranks of the homology of these Hurwitz spaces in a way that was polynomial in the number n of branch points and exponential in the degree j of the homology. These are not impressive bounds. They do require a bit of work, but to the eyes of a topologist, they're probably not the most impressive computation that you'll see. To improve these, to approach the second order term problems, we need to improve the bounds. And so that's what I'd like to talk to you about today. The tools in doing so are going to look very, even though this is now a problem in algebraic topology, the tools will be really very, very homological algebraic. So let me explain how that happens. So these Hurwitz spaces, there's a natural forgetful map from the Hurwitz spaces to the configuration space of endpoints in the plane. So there was a lot of data packaged into this definition of the Hurwitz space. We've got another curve, we've got a map, we've got an enumeration of the branch points, we've got Galois data for the, we've got data for the Galois group of the curve and information about the monodromy. We're going to forget all of that except for the branch locus. So if I have something that I know is branched at exactly n points, when I forget all of the information about the cover except for the branch locus, I get a set with n points, and that's precisely an element of the unordered configuration space of n points in the affine line. So this map is a covering space. The fiber is just the set C to the n, because I've forgotten the monodromy around the branch locus. But actually, that's all I've forgotten, because I can reconstruct the data of the branch covering if I know the monodromy around the branch locus. And so that allows us then to identify the homology of these Hurwitz spaces, say with coefficients in a field K, as the homology of the base of this covering space, the configuration space of endpoints in C, with coefficients in the vector space generated by the fiber, C to the n. So I'll write that as K square bracket C to the n. But notice that if I write V to be the vector space generated by the set C over K, so a single copy of C, then then the vector space generated by C crossed with itself n times is isomorphic to the n-fold tensor power of that vector space V. And it turns out that this vector space V is a particular example of something called a braided vector space. So this is a vector space over K with a self-map sigma from V tensor V to V tensor V. It's supposed to be invertible. And in this case, it's given by the formula, well, if G and H are elements of C, they're basis elements for this vector space V, then sigma of G and H is gotten by moving H past G but conjugating it along the way. So H tensored with G conjugated by H. So it turns out that this operation sigma satisfies the braid equation on the tensor cubed of V. And so that gives us an action of the braid groups on the n-fold tensor power, where sigma, the ith generator of the braid group, acts by applying sigma to the ith and I plus first tensor factors in that n-fold tensor product. So this is a beautiful representation that was discovered by Hurwitz. This is an alternate interpretation of what that representation looks like. So a theorem that that we proved in the paper on the moduli conjecture was an identification of this group homology of the braid group, which is the fundamental group of the configuration space. So the homology of this local system, or the group homology of the braid group with coefficients in this representation, this can be identified with an entirely different homological algebraic gadget. It's the cohomology, in the sense of the cohomology of algebras, of something called the quantum shuffle algebra, on not the original braided vector space, but a slightly different one. So what do? We take our original braided vector space, and we change sigma by basically just multiplying by a sign. So instead of sigma of G tensor H, I get being H tensored G to the H, we get sigma of G tensor H as negative H tensored with G to the H. So that's a new braiding on V epsilon. And then what we do is form the tensor coalgebra on W. So as a vector space, it's the sum over all n of the n-fold tensor powers of this vector space. And it's equipped with a multiplication which is dual to the co-multiplication on the tensor algebra. That is hiding a lot, because that multiplication is occurring in a braided monoidal category. And so if you're familiar with the multiplication on the tensor coalgebra in a usual setting, you're probably familiar with the fact that what you get is the shuffle algebra. So encoding the fact that the diagonal on the tensor algebra involves shuffles. The same is true here. However, because we're working in a braided monoidal category, those shuffles are replaced with lifts of the shuffles from the symmetric group to the braid group, and that defines a rather complicated multiplication on this quantum shuffle algebra. So this theorem in this paper identifies the homology, the jth homology of these braid groups with coefficients in these n-fold tensor powers of this representation. Sorry, this representation, which is the n-fold tensor power of the braided vector space, as the Ext algebra of the quantum shuffle algebra with trivial coefficients. And the bi degrees here, well, the shuffle algebra is graded, so it has an internal grading. That's this number m. And n minus j is the homological grading in Ext. All right, so our problem of studying the homology of the Hurwitz spaces got transformed into studying the homology of the braid group with coefficients in these representations. And that in turn got transformed into the computation of the cohomology of the shuffle algebra. So that's what we'll try to approach. But unfortunately, the cohomology of the quantum shuffle algebra is quite complex indeed. So what we're going to try to do is replace the shuffle algebra with a somewhat simpler analog, something called the Nichols algebra. So again, the shuffle algebra is the tensor coalgebra on W, and in particular, it contains W in degree 1. And what we'll do is define B of W, the Nichols algebra, to be the subalgebra generated by that vector space W. So an example which might be familiar is the following. If I start with just a vector space with a normal, with a symmetric braiding, so sort of unlike in this example where G and H, the action of sigma permutes them but conjugates them along the way, if it simply just permuted them, if sigma of G tensor H was H tensor G, then I would have this situation of a symmetric braiding. In that case, the tensor coalgebra, the shuffle algebra, is isomorphic to the symmetric algebra on the free Lie algebra on W's. So this is a consequence of the PBW theorem. Of course, this only works in characteristic 0, as we've stated it. But right, so the tensor coalgebra, the shuffle algebra is isomorphic to the symmetric algebra on the free Lie algebra on W. Now that's a very, very, very large algebra. It has infinitely many generators, assuming that W is at least rank 2. And the free Lie algebra itself grows in size exponentially in degree. So this is quite large indeed. But inside of it, we have the subalgebra, which is just the symmetric algebra on the degree 1 part of the free Lie algebra on W, just the symmetric algebra on W itself. And that subalgebra is precisely the Nichols algebra. So you should keep that in mind as a sort of guiding principle of what the Nichols algebra is like. That said, there are very few cases where the Nichols algebra has as straightforward a description as this one does. So we'd like to study the cohomology of the shuffle algebra using the cohomology of the Nichols algebra. And the way that we'll do this is by producing some spectral sequences converging to the cohomology of the shuffle algebra that start with the cohomology of the Nichols algebra. So what we can do is filter the shuffle algebra by powers of the augmentation ideal. And the associated graded then decomposes, it turns out, as a twisted tensor product of the Nichols algebra and some complementary factor. Now what that complementary factor is a little bit complicated to explain, and it's sort of related to the fact that explaining what the free Lie algebra is a bit of work. But in particular, it's generated in degrees at least 2, because we've already gotten all of the generators in degree 1 inside of the Nichols algebra itself. So what we can do is then study the cohomology of the shuffle algebra, which we want, by a May spectral sequence that starts with the cohomology of the associated graded of the shuffle algebra. But that in turn, because of this decomposition into a twisted tensor product, can be identified via a Cartan-Eilenberg spectral sequence with the cohomology of the Nichols algebra tensored with the cohomology of this complementary factor E. Now, this complementary factor is kind of hard to say exactly what it is because it's so large, and so its cohomology is also hard to describe. That said, what it contributes to the cohomology of the shuffle algebra in the after going through these spectral sequences will consist of classes in homology of the braid groups with coefficients and tensor powers of V, where J is at least degree n on 2 minus 1. So in some sense, to the eyes of homological stability, this part is really irrelevant. It's only producing classes that are very far outside of what we expect the stable range to look like. All right. So morally, we come away thinking that the cohomology of the Nichols algebra should contribute the dominant terms to the cohomology. And consequently, they'll also contribute the dominant terms to the point count of the Hurwitz spaces. All right. So what exactly does that mean? So there's a wonderful theorem of Kapranov and Shechtman, which came out at about the same time that we were doing this work on Malus conjecture, which gives a geometric identification of the cohomology of the Nichols algebras. So what they prove is that there's an isomorphism from the cohomology of the Nichols algebra. Now, before I say it, let's go back to our theorem, which they also prove a version of. The homology, the cohomology of the shuffle algebra is isomorphic to the homology of the braid group with coefficients in V tensor to the n, or equivalently the homology of the configuration spaces with coefficients in this local system given by V tensor to the n. And they prove the analogous theorem for the Nichols algebra. The cohomology of the Nichols algebra is the homology no longer of the configuration spaces, but rather of the n-fold symmetric product of C, or of the affine line, with coefficients in a sheaf which is gotten as a perverse push forward of the local system that we had on the configuration space, which is defined by this representation of the braid group. We do a perverse push forward of this sheaf to the symmetric product. And they identify the cohomology of the Nichols algebra with the homology of this sheaf. So that's a lovely geometric interpretation of what this piece of the cohomology of the Nichols of the shuffle algebra is, but what we'll do with this is notice that by its identification with the cohomology of a variety, or the homology of a variety rather, the right-hand side of this expression carries an action of the absolute Galois group of the field that we're working over. So in particular, if we're working over FQ bar, I get an action of the Galois group here, and consequently I get an action of the Galois group here. So the cohomology of the Nichols algebra supports a Galois representation, and moreover, the map from the homology of configuration spaces to the homology of the symmetric, the n-fold symmetric product is induced, which it corresponds to a map in the cohomology of the shuffle algebra to the cohomology of the Nichols algebra, which is dual to the inclusion of the Nichols algebra into the shuffle algebra. And the fact that this map of schemes is a map of schemes is telling me that it's Galois equivariant. And so, in particular, this map on the cohomology of these algebras is also Galois equivariant. So in particular, we get an action of the Galois group here, which is consistent with the action on the configuration spaces. And then if we go back to this theorem here, that the contribution of this complementary factor only lies in degrees bigger than n on 2, we come away with the fact that if I tried to run the point count on the Hurwitz spaces, which is to say, if I tried to run the point count on this Xed algebra, it's going to be the same thing as the point count, sorry, and I'm saying this too fast, the point count on the Hurwitz spaces by the Grothendieck-Lefschetz fixed point theorem is the same thing as the Lefschetz number for the action of the Frobenius on the homology of configuration spaces. But the sort of homological stability, or the such as it is, it's not really a stability, but it's a statement that the cohomology of E is somewhat negligible in low degrees. This tells us that the corresponding alternating sum of traces of Frobenius is also negligible on the part of this coming from E. So we come away with the statement that the point count of Hurwitz space, which is the Lefschetz number of Frobenius there, is the same as the Lefschetz number of Frobenius on the Nichols algebra, up to a multiplicative factor which is controlled by that complementary factor E, but that factor grows at worst as q to the 3n on 4. Q to the 3, which is to say it grows to the worst, at worst as the discriminant to the 3/4. And that 3/4 is related to this n on 2. All right. So what does that tell us? If we want to get a good approximation to the point count here, it sort of suffices to get a good approximation to the point count here. And in some sense, it should tell us that second order terms, at least up to degree 3/4 of the, at least up to discriminant to the 3/4, should be controlled by the Nichols algebra. Now I say this, we should be a little bit careful. If you go back, for instance, to the statement of the second order term for cubic fields, this was a additive difference. We've got x to the 1 and x to the plus something involving x to the 5/6. Whereas here, our expression is going to say something like, well, this might be controlling these terms up to multiplying by some power of x to the 3/4. So it's not quite the same formula as the kind of formulation as in the number field setting, but we hope that it will be still instructive in studying these second order terms. All right. So so we've sort of turned this problem into a computation about computing the cohomology of these Nichols algebras. So how do we go about computing those cohomologies? Well, at the very least, we can try to use some Koszul duality kind of tools in studying these Nichols algebras. So there is a surjective map from the tensor algebra on W to the Nichols algebra on W, because the Nichols algebra on W is generated by W, so certainly there's a map from the free algebra on W to it. So we can represent the Nichols algebra as the tensor algebra modulo an ideal, and then we can just study the quadratic cover of the Nichols algebra, which is gotten by simply quotienting by the ideal generated by the degree 2 part of the ideal that we had before. So you're just throwing away all of the relations in degrees higher than 2 that are not implied by those relations in degree 2. And from that, we can also form the quadratic dual algebra. So we often write this with a shriek. So we take the quadratic cover and then take the quadratic dual. That's the tensor algebra on the dual vector space modulo the quadratic ideal generated by the set of relations which are orthogonal to the relations here. So that algebra we'll call R, and it turns out that this is isomorphic to the zeroth homology of the Hurwitz spaces. So h naught of Bn with coefficients in V tensor to the n, by our formula from before, this is the cohomology of the shuffle algebra in diagonal degrees. And that's pretty easy to identify with the cohomology of the Nichols algebra in diagonal degrees. But we can definitely use some standard quadratic algebra tricks to identify the diagonal cohomology of an algebra with the quadratic dual of that algebra. So that's the algebra R. It corresponds to the ring of components of Hurwitz spaces. And the action of Frobenius is very well understood here. One simply counts the number of components of this scheme that are defined over FQ and multiplies by Q to the n. That's the trace of Frobenius on that on the nth term in this algebra. So that piece of the cohomology, the degree 0 part, should be what's responsible for the linear term in these, the linear, the first order term in these arithmetic statistics type problems. But we also expect that there should be more to the cohomology of the shuffle algebra. Unfortunately, there's very few computations of the cohomology of these Nichols algebras out there at all. But one of the very few ones was done several years ago by Drago Stefan and Christian Vai. So let's study this. This corresponds, in our language, they use a different language, that of the Fomin-Kirillov algebras. This corresponds to, in our setting, to studying the group S3 and the conjugacy class C of transpositions. So correspondingly, we're looking at simply branched triple covers of the affine line. Right. Their theorem was, if I work in characteristic 0, the cohomology of this Nichols algebra, which is also known as the third Fomin-Kirillov algebra, is isomorphic to its ring of components. It's the quadratic dual of that algebra, adjoined a single generator, and that single generator lies in by degree 4, 6. So cohomological degree 4, internal degree 6. When pushed through the topological machinery, that would then correspond to an element in the second homology of the sixth symmetric product, or the second homology of the sixth configuration space, depending upon whether it survives that spectral sequence or not. And that then would also correspond to, under Poincare duality, a class in the 10th compactly supported cohomology of the configuration spaces. So, and that's the only new piece of cohomology in this particular algebra. So we're led to a conjecture, which is a very hopeful one, and it might be naive, but that our first conjecture is a purity conjecture, that the action of Frobenius, which is constructed on this algebra via the theorem of Kapranov and Shechtman, is such that Frobenius acts on this generator by multiplying it by the only thing that we could imagine that it would multiply it by, which is q to the fifth. So we know from Deligne's bounds on the eigenvalues of Frobenius that the eigenvalues here are bounded in norm by at most q to the fifth. So we're going to we'll go with the hopeful guess that it's in fact exactly q to the fifth. And furthermore, we'll ask a second conjecture, which is that the multiplicative structure here is Frobenius equivariant. So that is, if I want to, that Frobenius acts as a ring homomorphism on this cohomology. This may be a little bit naive. There are good reasons to believe that this is a little bit naive, but one possible guess that would be a little bit more refined is that it might act as a ring homomorphism on the G invariant part of this algebra. So if this is true, then we know from this argument exactly how Frobenius acts on R, and we know from our conjectures how it acts on every power of x, and so we can actually just compute the Lefschetz number of Frobenius very directly. It's the sum, so in degree n, it's the sum in all degrees adding up from 0 up to 1/6 of n. That's because that 1/6 because x lies in sim 6 of the number of points on Hurwitz space that are that's supposed to be the number of components which are defined over fq times q to the 5k, where here we're in degree n minus 6k, and then we get the q to the 5k from, this is corresponding to the class x raised to the kth power. So those are all of the terms that contribute to the homology of the nth term here by adding up from k equals 0 to the floor of n on 6. And now the number of points that are the number of components that are defined over FQ is basically 1. So with a little bit of fussing about, you can sum this series, and it's approximately equal to q on q minus 1 times q to the n minus q to the 5/6 n. And now I really want to urge you to regard this as like 1 over zeta of 2, this as sort of the linear term, and this is the second order term in this kind of expression. All right. So that was what we can extract from the Stefan Weil result, along with various conjectures about how Frobenius acts on the cohomology of the Nichols algebras. So we could ask about other groups. And one thing you can do is, well, we started the Koszul complex process here in the previous setting. Let's build the Koszul complex associated to the Nichols algebra. So I'll take the dual of the Nichols algebra and tensor it with its quadratic dual, and equip that with a differential, which on the R part multiplies by a basis of the generator of the generating vector space, and in the Nichols algebra direction, it does the dual operation. It's the operation dual to multiplication in the dual algebra. So that's written as partial sub VI. This is the Koszul complex of this algebra, and it's not terribly hard to show. We do in the paper on the Mala conjecture that the cohomology of the Nichols algebra is a subquotient of the ring R tensored with the shuffle algebra on the homology of the dual Koszul complex. So, there's quite a lot of possibility for differentials here, but the moral of this is certainly that the homology of the Koszul complex really controls the growth rate of this shuffle algebra, or the cohomology of the shuffle algebra. And if these conjectures about how Frobenius acts hold, if I understand the cohomology, the action of Frobenius on the cohomology of K, then multiplicativity should tell me I can figure out how it acts on this tensor coalgebra. And hopefully I could also get some idea about how the cohomology acts on the dual Koszul complex by some sort of purity argument. So if that all goes through, then it should control the point count up to, discriminant to the 3/4. Again, that 3/4 is the same 3/4 as in this expression. So to revisit the one we just talked about, when we're looking at S3 and transpositions, the Stefan Weil result proves that this homology is the homology of this Koszul complex is concentrated in 1 degree, 1 bidegree. It's a single generator X in bidegree 4,6, and the 5/6 that we had here should give rise to a discriminant to the 5/6 term, which is consistent with the second order terms due to Taniguchi-Thorne and Bhargava-Shankar-Tsimerman. There is definitely a lot that we're leaving out here, particularly about the constants involved, but that's an indicator that this second order term is at least the fact that the second order terms that we're getting are consistent across the number field and function field setting suggests that indeed these conjectures are perhaps reasonable. So Alexander has computed a lot of the homology of the Koszul complex in the case of when we move from S3 to S4, but keep simple branching in the conjugacy class of transpositions. Just as in S3, there's a class, in fact, there's at least 8 classes in bidegree 4,6, but there's also a new class in degree 4,8. And just as before, the 4,6 term should give us a second order term of the form x to the 5/6, And if it's meaningful, and I'm not sure that it is at this point, but this new term should produce a third order term of the form x to the 3/4. Now that very well may be noise, since our our control over the cohomology of these shuffle algebras can only control the second and third order terms up to something like x to the 3/4. So it might actually just disappear into the error. That's hard to say at this point. Greg Michael has spent a lot of time computing the cohomology of these Koszul complexes, where instead of looking at symmetric groups, we're looking at dihedral groups of order 2p, where p is a prime, and also looking at the elements of order 2, the reflections there. So he's found, and this is also somewhat preliminary at the moment, he's found that the homology of the Koszul complex is, much as in the S3 case, generated in a single bidegree. Here it's 4, 2p, and again, if you play with the numerology of what the Deligne bounds suggest, the contribution should give you, if the purity conjectures go through, that would give us something like a second order term in degree, x to the 1/2 plus 1 over p. Now, of course, as p gets very large, this also moves into the error term kind of area, but we do think that these sorts of computations might be predictive of what we should expect for these kinds of problems, even in the number field setting. All right, that's, I think, about all I had for you. Thanks very much.